All right, chapter 4, section 3, solving quadratics using square roots. So we're running into this common theme here, this solving quadratics. So in general, our answers are going to be x equals something. And just to recall us back to section 2, where we dealt with this visually, there are 3 families of answers that we're going to run across. Now, visually, when I have a parabola, a quadratic, that U shape, I could have 3 possible sets of solutions. Either I could have 2 solutions, basically where that U shape crosses the x-axis twice. Okay, we're going to see how that pops up algebraically in this section. And then another way is that I could have that parabola, that U shape, only touching the x-axis once. That would just be a very special case where just the vertex, the most extreme point of a parabola, is the only thing touching that x-axis. And finally, I could have the parabola, the U shape, completely miss the x-axis, and that would be an example of no real solutions. And again, we're going to explore how to do this algebraically in this section, and instead of looking at a graph and just looking visually to see where it crosses the x-axis, we're going to be seeing how we can solve for the variable, solve for x in this case, by algebraically moving stuff away from it, and what those answers would look like in terms of those same 3 families of results. But before we begin, there's one kind of main asterisk here to point out, and that's that this technique that we're going to be learning, and we're going to learn several techniques throughout this chapter, but this one in particular, this section, is a special instance where in a given quadratic equation, b will equal 0. And that's just a fancy way of saying that there's going to be no single x term right here. So if I ignore this x term right here, I'm left with just an x squared term, and then the possibility of some other number. Okay, and this is an important concept right here, because my job ultimately, when I'm asked to solve something algebraically, right, and I have to use inverse operations to move stuff away from that x, the problem is if it's written like this, as an x squared plus bx plus c, if I have an x term and an x squared term, obviously, like what we've learned in the past couple chapters, these 2 terms are not like terms. They cannot mix. I can't combine an x squared with an x and vice versa. So if my job is to get x by itself, if I were to try and get this x by itself and move this x squared to the other side of an equation, I would end up with an x on both sides of an equation. And the same thing goes if I tried to move stuff away from the x squared. Not only can I not combine them as they are, but I also can't isolate an x without having another x on the other side. So this section is going to focus on results where there is no x term. Instead, I'm just going to have an x squared term and then other numbers. And that will be important moving forward, because that means I algebraically can get that x by itself. All right. And so you'll have it here in the margin, but these are kind of the scenarios that you're going to get if they're written in standard form. But again, there will be no x term. You're going to see x squareds, and that makes sense because we're still dealing with quadratics. If there were no x squared term, it would no longer be a quadratic. So we will see that. But this will be the process of moving stuff away from the x squared, isolating that, and then taking the square root of each side to get that x by itself. And so that leads me to this next point. So basically our job here, whatever kind of version of this we're going to get, my job is to first get x squared isolated. Basically solve the equation for x squared. So I should get x squared equals some value, whatever that value may be. We'll use the letter D here to just represent whatever value, whatever number that may be. Okay, so I have x squared equals some number as a result. Now, as I said before, as we talked about in section 2, there are kind of 3 families of answers, of different outcomes I could get here. And the same is going to be true here algebraically. So for instance, if this other number is some positive number, okay, whether it's a weird decimal fraction or a nice convenient whole number, if it's a positive version of that, so if d is bigger than 0, that's going to represent my 2 real solution scenario, the first family of answers, 2 real solutions. So visually, what that would look like from section 2 would be my U shape, my parabola would cross the x-axis twice, right? And those values will be represented by whatever the square root of d is. Now you're going to notice a new symbol here. And this tends to be the one curveball here in this section from previous chapters, previous units, previous years. We're used to taking a square root, but we're not used to this symbol as much. This symbol is plus or minus. Okay, that's why we see both symbols right there. And what it implies is that whatever my result is over here, I'm going to have the positive version of it and the negative version. That's why I get two real solutions in this case, both the positive and the negative. And here's why. When I take the square root of something, like say 9, when I take the square root of 9, our gut reaction there is to say like, oh, well, the square root of 9 is 3. And that's absolutely correct. And the way I could confirm that is if I were to square 9 or multiply, if I were to square 3 and multiply 3 by itself, I'd get right back to 9. That's why I know that 3 is the square root of 9. And it's usually where we would have stopped in the past. But there is another possibility, -3. Because think about it for a second. If I were to take -3 and square it so that I had -3 times -3, the negatives cancel and I get right back to that 9. Meaning that both the positive and the negative version, as long as I square it, I'm going to end up with a positive result. And so if I ever take the square root of a positive number, technically speaking, mathematically speaking, both the positive and the negative are results. And that's why I get two real solutions there, both the positive and the negative. All right. So what happens if this number, this value I've isolated, I've done the work to isolate x squared. What happens if it equals 0? Then that's going to represent my one real solution. Because if I were to take the square root of both sides, but if I take the square root of 0, well, there's only one value that would pop out the other side. You could say plus or minus 0, but plus 0 or minus 0 is the same exact value. It's 0, meaning that there's only one real solution. That would be an example visually of that U shape, that parabola only touching the x-axis in its most extreme spot, its vertex, a single point. Okay. And then lastly, what happens if this value is negative? However weird the number may be, if it's a negative number, then if I were to try taking the square root of both sides, this is where I would get no real solutions. Because you could try this on your own. On your calculator, you could try to take the square root of a negative number. Your calculator will spit out an error message. That error is that there isn't a real number. There isn't some decimal or fraction that I can take the square root of a negative number and get, because there's nothing I can multiply by itself to get a negative result. It would require that one of the things I multiplied was negative and the other was not. But then it's no longer squared. It would be some value multiplied by a negative version of that value. Okay, so this result, if d is less than 0, if d is negative, whatever value here is negative, that's going to be no real solutions. Visually, that would be the equivalent of me drawing a parabola, that U shape, and completely missing the x-axis altogether. A happy face above the x-axis or a sad face well below the x-axis. No x-intercepts, no solutions. And so for us, algebraically, that's going to be if I ever have to take the square root of a negative number. All right. We'll learn later in this chapter what to do with the square root of a negative number. There is a mathematical answer. It's just a completely different family of numbers. That's why they throw in this word real into each of these solutions, right? No real solutions. There are what we call complex solutions or imaginary solutions, but we'll deal with that later in the chapter. For right now, just suffice it to say that if I ever get x squared equals a negative value, then it's going to be no real solutions. And you'll see that in your drop-down menus on Big Ideas. All right, so let's go into some examples. So just to kind of show you visually what you're going to see as far as problems in this section. And this will be very similar to what you see throughout this chapter. You're going to be seeing a quadratic equation. There will be an equal sign, and typically it's going to equal some value, whether it's 0 or some number, doesn't matter. Okay. One thing you'll see missing from each of these equations that we had in section 2, and we'll have in future sections as well, is that there's no x term. There's no single x term. And you may think like, wait, there's a single x, but you'll notice that's part of a parentheses that is also squared. So there is an x term that will be squared if I were to distribute this. But in any case, all of these have the x squared. That's why it's quadratic, but you're not going to see a single x. Again, that being the exception to the rule, but technically it still is an x squared, right? And that's important because when it comes to solving these quadratics using this method, using square roots, it's important that I not have an x because I need to get the x squared by itself with no other x term. I need to isolate that x squared. All right, so let's go through technique. All right, so for all of these problems that you're going to see in section 3, you're going to be tasked with doing the same exact thing. You're going to be asked to solve. That will be the instruction at the beginning of all these problems and moving forward into this chapter. Solving literally means that whatever answer you get, you're going to be ending up with x equals some value, right? So our first problem, we're given this quadratic, 3x squared minus 27 equals 0. And it will tell us to solve the quadratic. It might use the language in this section to solve this quadratic using square roots. I'll point that out when we get to that step. But here, for those that need like in your margins, like some sort of like step list, checklist, a process, whatever it might be, your first task is this: get x squared by itself. Get x squared by itself. And again, it's important that there's no other x here because we'd run into problems of not being able to combine the x's together and not being able to isolate either of the x's. But in this case, we can isolate this x squared by moving away this negative 27 and ultimately that 3. And so this will be very familiar, hopefully very comfortable with you for things that you've done in the previous years, whether Math 1 or middle school. But this ends up being the same exact process we've done then. So if I want to move this negative 27, the inverse would be to add the 27 to both sides of the equation. And the reason we do it to both sides of the equation, if you think about like a balance, a teeter-totter, a seesaw, if I had people sitting on both sides of that balance point, that equal sign, if I gave the same weight to each side, nothing would happen. It would remain its balance. So I can't just add it to one side. I have to make sure to do it to both. And so when I do this, on the left-hand side, I'm left with just 3x squared. On the right-hand side, when I add 27 to 0, I get 27. One step closer. So I'm still needing to isolate this x squared, so I need to move this 3. The 3 is multiplying by the x squared, so the inverse operation here would be to divide by that 3. But I have to make sure to do it both sides to remain balanced. And now when I divide both sides by 3, sorry, let me get this centered. All right, when I divide both sides by 3, on the left-hand side, I'm going to get x squared by itself. That's the whole reason we did those operations. We have officially isolated x squared. And then on the right-hand side, when I divide 27 by 3, I get a nice friendly 9. All right, so again, step number 1, get your x squared isolated. Now, this is where we get the namesake for the name of our section. Solving quadratics by using square roots. Now, up until this point, we've used pretty traditional arithmetic inverses, basically addition versus subtraction, division versus multiplication. Okay, but now if I want to get rid of a squared element, we've learned this recently, but the inverse, to undo a squared, I need to take a square root, a radical. But I got to make sure to do it to both sides because, again, I need balance. So when I take the square root of both sides, on the right, I'll be taking a square root of 9. On the left, I'll be taking a square root of an x squared. What will ultimately happen here is that the square root will undo the squared, and I'll be left with just x. This is using square roots. So it's important that I first isolate x squared so that I can use this square root technique, because before I wouldn't be able to use the square root because I'd have to do it to the entire side, and it makes things really complicated. So the first task is to get x squared by itself. Now that I have it by itself, now I can take the square root of both sides, and here's what will happen. Now here is where a lot of students tend to make mistakes because they oversimplify. They're like, all right, the square root of 9, that's 3. Done. But no, that's not, that is true, but that's not the only answer here. Yes, the square root of 9 is 3, but here's again what we'll need to understand. Negative 3 is also a solution. Because if I were to go backwards from either of these results, I should be able to square both of these to get right back to positive 9. Well, most of us will understand inherently that 3 squared will get us back to 9. That's why the square root of 9 is 3. Negative 3 is also the square root of 9, though, because if I were to square negative 3 and do negative 3 times negative 3, the negatives will cancel, and I'll get back to that positive 9. That's why these will end up being the solutions. Now, just to kind of relate this back to the symbol that you saw before, I could also write this as x is equal to plus or minus 3. That is a correct way to write this. That's absolutely an okay thing to do. This represents those two solutions. Another way we could write this as x equals 3 and x equals negative 3. You'll probably see various versions of this in your Big Ideas assignment. But this is the result. And so visually, what would this look like? So here's where I'm going to share screen, and I'm going to show you on Desmos.com what would happen, similar to what we did in section 2, just to kind of confirm our result. All right. So right now I'm sharing screen, and you'll see Desmos pop up. And so if I were to go into my function table right here and input that equation that we just did, 3x squared, there's the 3x squared just as it is. That represents that kind of steeper U shape that recalls us back to chapter 3. But then if I were to subtract that 27, here is that parabola. All right. Now I can zoom out so you can kind of see that U shape. There's out. It goes way down below there, intersecting at negative 27 down here. But more importantly, what I want you to understand is that visually, you will see two solutions. Okay. Two places where it crosses the x-axis. Negative 3, positive 3. Lo and behold, if you look back at the whiteboard up here, right, you're going to see positive 3 and negative 3 as those solutions. We just did it algebraically in this case using square roots, whereas in section 2, we would have used our graph to find those results. All right, let's do another one. All right, so for the record, as I'm erasing this, parts B and C, I'm going to skip right now. The solutions are going to be on Google Classroom, but parts B and C will represent what happens. It's the same exact process. It'll look exactly like part A, just different number values. But the process is exactly the same, still moving stuff away from x squared and ultimately taking the square root of both sides. But what you'll find in part B is you'll take the square root of 0. That will give you a single result. So that would be visually the equivalent of just the vertex being located on the x-axis. And then for part C, you're going to do isolate the x squared, move stuff away from that x squared. And then when you take the square root of both sides, you're going to end up taking the square root of a negative number. And as I said before in the beginning, when you take the square root of a negative, there is no real solution. That is the equivalent if you were to graph that parabola of it, that parabola completely missing the x-axis. There are no intersection points. So that's what you can expect in part B and C. But I'm going to skip ahead to part D. So this was the 4th example. And I wanted to do it because it's just represented a little bit differently in that you will have this parentheses squared equaling some number. All right, so parts A, B, and C are all just like that last example we did, right? Pretty traditional, like moving stuff away through inverse operations. In this case, we're also going to use inverse operations. It's just presented differently in that now I'm going to be doing something else. All right, so my task is still the same. In order to solve, I got to get x by itself. So if you see a problem like this, and you'll see a few on your assignment, the first thing actually you need to do, if you need to write that little checklist on your side, right? If there's any numbers added or subtracted after this parentheses squared, so these will be pretty easy to identify when you come across them. But if ever you had this parentheses squared, if there are ever any added or subtracted numbers after that, move those away first and get this parentheses squared isolated. This is the equivalent of isolating the just x squared, because technically you have isolated the x squared. It just happens to be locked away inside of a parentheses. All right. So again, if there are any other numbers added or subtracted here, move those away first. Inverse operations. Now, what I'll do is instead of trying to move away this 1 first, because it's locked away inside the parentheses with the x, the first thing I'm actually going to get rid of is the squared. And here's again where I'm going to take the square root of both sides. So this technique is slightly different in that I'm going to be doing square roots before I end up moving every piece away from x. And when I take the square root of both sides, on the left, I have this really complicated looking thing where I have the parentheses squared that I'm taking the square root of. And on the right side, it's a little friendlier, square root of 25. But again, the whole reason I do the square root is to undo, to do the inverse of this squared. And what I'll be left with is just the parentheses, x minus 1, or just x minus 1. On the right-hand side, this is one I can actually take the square root of. And just for the record, when you get to this part where you're taking the square root of some number, in this case, it's nice and friendly. There is a square root to 25. That's a nice whole number, right? But also keep in mind, you may end up with different numbers here that you can't take the square root of comfortably. And so that then it's just a practice like what we did in section 1, simplifying a radical, right? If it's not a perfect square itself, see if a perfect square can divide into it, just like we did in section 1. But anyway, this one ends up being friendly. The square root of 25 is 5. That's the gut reaction. But again, one thing I want to point out is that we have to get used to this new element, that technically speaking, there are 2 results here, both positive and negative, because positive 5 squared is 25, but also a negative 5 squared gives me a positive 25. So both of these results, these represent the 2 possible solutions. Okay, so far, so good. We've gotten rid of the squared, but technically speaking, x is not by itself yet. We now have to move this 1, but here's where we run into a little bit of an issue. Now I technically have 2 different numbers on this side. Okay, so this is from when we dealt with this with like absolute values. But what we're going to do right now is we're going to break this up into 2 equations because, again, technically I have 2 different results here. My first equation being x minus 1 equals positive 5. Right? And I can move that 1 to the other side to get that result. My second equation here will be x minus 1 equals the negative 5. Again, the reason why we have 2 results here is because when I took the square root of 25, both the positive and the negative versions can be the results from that. So we get to this spot, we have our 2 different results. And in both cases, if I want to isolate x, I'm going to move the 1 the same exact way. It's being subtracted, so I'm going to add 1 to both sides. Nothing terribly complex in and of themselves, but what I'll get here is that when I add 1 over here, x equals 6. And over here, when I add 1 to both sides, x is going to equal negative 4. These will end up being my 2 solutions. All right. So before I jump over to Desmos and show you visually what this would look like, because these will be the 2 intersection points, positive 6 and negative 4. The other thing I want to point out algebraically is if I were to take either of these numbers, 6 or negative 4, and plug them back into the original equation up here, it should also check out. It should also make sense. So for instance, if I were to take positive 6 and replace x with positive 6, 6 minus 1 is 5. That 5 squared gives me 25. That one checks out. That's definitely a solution. Now, if I plugged in the negative 4 for x, negative 4 minus 1 gives me a negative 5. That negative 5 squared, or negative 5 times negative 5, gets me back to positive 25. Both answers check out. So let's see what would happen on Desmos, just to kind of confirm visually what it would look like. So let me get rid of this old one. All right, so now if I were to input that function, again, just as it's written, I'd have that in parentheses x minus 1 squared. Oops, not there. I need to finish the parentheses. There we go. Squared, right? There's my parabola. There's the parabolic U shape. And then it said equals 25. Now this is just as it's typed in. You'll see those 2 parallel lines right there. Those represent the 2 solutions, and you can see them as that negative 4 and positive 6 right there. Or if I were to take that 25 and subtract it to the other side, I'll actually see the actual parabola itself. Oops. So let me read that. Minus 1. There we go. Squared. And then now if I were to subtract that 25 to the other side, now there's the actual parabolic shape. Okay. There's that U shape. But again, importantly, where it crosses the x-axis, it does it twice. They're at negative 4. They're at positive 6. And again, if you were to look back at the whiteboard here, those are our 2 results, positive 6, negative 4. All right, let's do one more. Let me stop sharing. And we'll do one more example. And the only reason I'm going to do this other example is so that you can see what happens if I don't get a friendly solution. And I'll just do this one algebraically. I'm going to skip doing it on Desmos because, you know, you've seen how to do it now. But in this last example, the 5th one, we get 4x squared minus 13 equals 15. So this looks like part A. This looks like the same one we started with. And the techniques are exactly the same here. I just want to show you what happens if you don't get a friendly result. All right, so my process is the same. I need to get x squared isolated. So I got to move the 13 and I got to move the 4. The first thing to move would be 13 by addition, since it's being subtracted, whatever the inverse operation calls for. And so on the left-hand side, I'm left with just 4x squared. On the right-hand side, when I add 13 to 15, I'm going to get 28. All right, well, now I got to move the 4. The 4 is multiplying by the x squared, so my inverse here would be to divide. So I divide both sides by 4. And when I do that, on the left-hand side, the 4 goes away, and I'm left with just x squared. On the right-hand side, 28 divided by 4 gives me a positive 7. All right, so we've officially isolated the x squared. It equals some number. So now, just like before, I'm going to take the square root of both sides. On the right-hand side, I'll be taking the square root of 7. On the left-hand side, I'll be taking the square root of x squared, thus getting rid of the squared. And I'll be left with x equals the square root of 7. Now, here's where we run into a slight problem, because unlike before, we had nice friendly numbers here. There I just end up with nice whole number positives and negatives at this point. Now, I'm still going to end up with a plus or minus. That will be an important thing to understand. I'm still going to end up with a plus or minus. But now this becomes a game like what we did in section 1. 7 is not something I can take a perfect square of. All right? 7 is not something I can take a perfect square of. If I were to do that in a calculator, it would give me like 2.65 something. Or 2.64, yada, 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 right? The next thing I would technically check for at this point to simplify it would be, are there perfect squares that go into 7? And the answer is no. So this is going to be as simplified as it gets. So technically my final answer here would be this result, plus or minus the square root of 7. But that's just something I want to remind you that in section 1, we learned how to simplify these radicals. And so just be aware that that will also be required of you in this section. But I also wanted to point out that if it did say to round your answer to say like the nearest hundredth, okay, then you could just literally do this in a calculator, and this is the result you would get. You get x is approximately, since we were rounding here, but if you round to the nearest hundredth, you get about 2.65. But please keep in mind, again, because of the plus or minus, not only is 2.65 squared going to give me back to 7, but also, and there's the negative version of that number, because the negative times itself will give me a positive, and I'll get right back to the same result. So if it asks you to round to the nearest hundredth or something like that, then just be aware you're doing that calculator work. Otherwise, this would be what we call the exact solution, the simplified version of the radical. And again, you can double check this on Desmos. If I were to graph this, you would see intersection points at both 2.65-ish and negative 2.65-ish. It's just that, again, one thing I want to emphasize from section 2, this idea of visually interpreting what you see on your graph, ultimately, particularly in this case, where it would give you these decimal results. These would be what we call approximations or estimates, because ultimately we're cutting off a bunch of the decimal parts, whereas this would be technically the exact solution, a far more accurate representation. All right, I'm going to stop recording.